Hello everyone. So we were discussing about the linear time invariant system. Okay, so we were in the last one we have discussed in the last about the linear time invariant system for the discrete time system. So in which we are going to today we are going to discuss about the stability of and causality. Okay, stability and causality of linear time invariant system in terms of impulse response. All right, impulse response. Now, what is simply stability? Stability is in a time domain system is simply a discrete time system is bounded input, bounded output, stable. Okay, stable. If and only if its impulse responses, its impulse, its impulse response, impulse response is absolutely summable. Okay, so this is what is stability. And what is causality? Causality is simply this, that when the system depends upon the previous input or the present input, not on the future inputs. All right. Its response. Okay, so let's move forward. And so the output of a linear time invariant system can be expressed as the output of a LTI system. The output of a LTI system can be expressed as yn. Okay, this should be equals to what? This should be equals to summation of k is equals to minus infinity to infinity hk x n minus k. Magnitude of this should be less than or equal to summation of k is equals to minus infinity to infinity hk. Okay, magnitude of hk and x n minus k. All right, so for bounded input xn, for bounded input xn, okay, for bounded input xn, magnitude of xn should be less than or equals to beta x less than infinity. Okay, okay, so beta x simply what? Beta x is some finite value. It is some finite value. Why it is some it is finite value? Because fixed or positive finite value, because for the system to be stable. Okay, a system can be stable only and only if for the bounded input sequence produces a bounded output. Okay, for bounded input it produces a bounded output sequence. Okay, for the input xn, for input xn is bounded if there exists a fixed positive value beta x. Okay, so when there is some fixed value beta x, this must be less than infinity. This is some finite value. All right. Now further, let's do the analysis of a discrete time. Let's write down over here, analysis of a discrete time linear time invariant system in the Z transform domain. In the Z transform domain. Okay, so let's see. So it was earlier stated that a linear time invariant system, LTI system, okay, can be completely characterized, can be completely characterized by its impulse response Hn. Okay, its impulse response Hn. Hn is the impulse response. So the output signal signal Yn of the linear time invariant system of LTI system, output signal Yn of the LTI system, and the input signal Xn are related by convolution, are related by convolution as Yn, this should be equals to Hn convolution of Xn. We have already studied that. Okay, so taking the Z transform on both the side of the equation, taking Z transform on both the side of the equation and using the convolution property, we will get what? We will get capital Y Z, this should be equals to Hz Xz. Okay, indicating Z transform of the output sequence. Z transform of the output sequence Yn is the product of Z transform of impulse response Hn and the input sequence Xn. Okay, what does this show? This is shown above. Okay, so the quantities Hn and Hz, the quantities Hn and capital Hz are two equivalent descriptions of system in time domain, are two equivalent description are two equivalent domain are two equivalent description in time domain and Z domain, okay, respectively. So the transform Hz is called, so the transform Hz is called the transfer function or the system function. Okay, it's called the transfer function or the system function, and it is expressed simply as Hz is equals to Yz upon Xz. Okay, or this can also be represented as, or equivalently it can be expressed as Hz. Yz can be represented as, from k is equals to 0 to some value m, bk z inverse k, z to the power minus k upon 1 plus summation of k is equals to 1 select n, okay, ak z minus k. Okay, where constant ak and bk are real. Okay, so the above transfer function is the ratio of polynomials in z inverse, okay, in z inverse, and hence it is a rational transfer function. It is a rational transfer function or system function. It is called or system function. So when you have studied about the signal system, you must have also seen some values of very basic unit step function, impulse function. Okay, so these type the z transform, all these things, cosine function and sine function, you have calculated that. All right, so for further problems which you are going to solve, all those things will also be helpful for you. Okay, so what are the poles and zeros of a transfer function? So as you all know about in the control system also, you have studied that the zeros of a system function hz, this is the function hz is mentioned over here, are the values of z for which hz is equals to 0. Okay, while the poles are the values of z for which hz should be infinity. You know that zeros are that for which hz should be equals to 0, and poles are what, for which hz should be equals to infinity. Okay, so since hz is a rational transfer function, the number of finite zeros and the number of finite poles are equal to the degrees of numerator and denominator. All right, these simply depend upon the degrees of numerator and degrees of denominator. Okay, this is the earlier concept which you have studied in the transfer functions. Okay, in the control system also. Okay, now little more explanation if you want in this hz, where it comes from, then you can easily see that simply we have the equation of a system which is described by LCCD equation. Okay, linear constant coefficient difference equation. Okay, linear constant coefficient difference equation, which is simply given by k is equals to 0 to n a k y n minus k. Okay, and this should be equals to k is equals to 0 to capital M b k x n minus k. Okay, so if you want to take the z transform of the above equation, then you will see that it will become k is equals to, after taking z transform of the above equation, it will become k is equals to 0 to capital N a k z inverse of y z. All right, and this should be equals to k is equals to 0 to capital M. Okay, b k z minus k capital X z. Okay, or if you want to write this, then you can write down this as also k is equals to 0 to n a k z to the power minus k y z. Okay, and this should be equals to k is equals to 0 to m b k z to the power minus k x z. Okay, so the system function for the system that satisfy a difference equation of the required form is you can write down this as hz. Hz is simply equals to what, yz upon xz. We have seen earlier, so this should become equals to yz is over here, xz is over here. Okay, then this come over here, then what should you will get, summation of k is equals to 0 to m. Okay, bk z to the power minus k divided by summation of k is equals to 0 to n a k z to the power minus k. Okay, and this you can also write down as if you want to find out the poles and zeros from this, then simply b naught upon a naught, if you are going to put the value of 0 over here, you will get b naught. 0 when it will be there, it will become 1. So b naught comes out from numerator, and a naught comes out from denominator. It will become is equals to simply summation of k is equals to 1 to m. This will become 1 minus, we can write down as 1 minus ck z to the power minus 1 upon not the summation, it is simply written in the poles and zero form. So we should write this like this. Okay, from k is equals to 0 to 1, 1 to m. Okay, poles are over here, and for the zeros we can write down as from k is equals to 1 to capital N, it should be 1 minus dk set to the power minus 1. All right, so each factor which is 1 minus ck z inverse in the in the numerator, just simply contributes 0 at z is equals to at z is equals to what, ck. Okay, if z is equals to ck, then it will contribute in zeros. You understand that if z over here is equals to ck, this will become 1. 1 minus 1 is equal to 0. All right, and pole at z equals to so each factor of this 1 minus dk z inverse contributes a 0 at z is equals to 0, and a pole at z is equals to dk. Okay, so it will contribute 0 at z is equals to ck, and a pole at z is equals to 0, it will contribute 0, it will contribute 0 at z is equals to 0, and pole at this. All right, so this is very a bit of confusion over here. Okay, so the stability and the causality for the z transform, stability, now the stability and causality for z transform. Okay, for z transform now we will discuss on next round. All right, so thank you.